actually it is basically a talk about estimating variance components in random effects model. So if you really want a gist précis of this, this is something which we actually teach at a like master's level. Many of us, lot of you have probably seen this before, and it is actually about mixed effects models, and we actually talk about variance components. There are several ways of uh, trying to estimate this, but this the mixed effects model tend to be a very exciting area and uh, a very active area in statistics. I will share some of the recent applications where this what I am trying to do is going to be relevant in a moment. So this is a joint work with Tatsuya Kubokawa, who is actually a very well-known guy in random effects models, and Shonosuke Sugasawa. Both are in University of Tokyo in two different departments, and so Sugasawa was a student of Tatsuya. Anyway, so let's look at what we are going to talk about. So what we are going to talk about is, as I said, was a mixed effects model. It's a very popular model in with many applications in statistics, especially if you are actually have your too many effects. Like if you think about, there are standard text in there, standard text in mixed effects models. This the history of this model goes back to like almost the beginning of statistics to the 1950s. So it is actually been very what should I say, this model has been studied a lot. So frankly speaking, when we actually looked at this, what we are going to describe, the first thing we wanted to find out that has not this been done before. I mean, that was the thing. Okay, things are, what we are going to do is basically very simple, but we were really surprised that it was not done. So the point about random effects model, mixed effects model, is that they have been used in modeling high dimensional big data, predicting summary values of variable of interest of predefined areas. So these two are two different applications. So frankly, if you have lot of groups whose mean you need to kind of model, you basically use a random effect model rather than estimating the same mean. So that's basically one of the use. Another use of mixed effect model has been to put dependence on different data sets, put the dependence in the model. I will show you that how that comes in, but that is basically where the application that I am going to talk about comes from, and that is actually from what is called a small area estimation. So one of the good thing about mixed effects models are that it often produce accurate predictors than the fixed effect model. So you have some fixed effect model, you have some error residual term, but you are kind of using those residual term and some kind of dependence between them to make your prediction a bit more accurate. So the optimal predictors are functions of error variance as well as the variance of the random effects. And as I said, the estimation of variance components have been has a long history in broad terms. So, and it goes back to like Henderson's. If you look at the book by Searle, there has been lot of methods of doing that. In broad terms, the estimators are mostly based on either analysis of variance estimator, which we call the ANOVA estimator, which we will be talking about. Like it is basically Henderson. Searle has a book on variance components. If you can wait through it, it's a very carefully written book, and you can go through it. Or basically what is called a minimum norm quadratic unbiased estimator, or called MinQ, which was actually studied by C.R. Rao and Clef. There is a book on that. Then there are maximum likelihood estimators like Hartree and Rouse 1967. Anderson had some papers on that. Miller had some papers on that. And then there were another thing called maximum restricted maximum likelihood estimator, which essentially kind of turns the model in some way such that you don't really need to estimate the fixed effect. You can just concentrate on the variance components. Okay, so the variance, so the main thing about ANOVA based method is that they are actually constructed from various residual sum of squares. So when you really talk about variance components, you are essentially looking at different kind of residual sum of squares with different components taken out of it, and from that you essentially estimate your variances. Good thing about this, these are available in closed form, so you can actually compute them. They, and it does not really require, if you really computing a maximum likelihood estimator or mean q estimator, it's basically can be solved in a numerical iteration procedures, and that has that can lead into problems. They are not always very stable, but ANOVA estimates can be actually done in terms of residual sum of squares. They are have closed form solutions, and they have nice properties. They have nice properties. People have actually said it is actually kind of well known that maximum likelihood estimators are going to be more, in general, are more efficient than the uh, ANOVA estimators, but that is not always very true. It's not very easy to check that that actually happens, but usually it is known that it happens. But on the other hand, ANOVA estimators are quite easy to compute, and that's why they are still pretty popular in many literatures. Let me actually go through one example. Okay, I will come back to an example what I mean by small area estimation. That will be clear. So what I actually will talk about, my basic model is what is called a nested error regression model. It was, or sometimes in small area estimation literature it is called unit level data model. I will get back into small area estimation in a moment. So what you really have here is that you have a Yij, that is the ith of jth observation, jth response in the ith group, and then you write it as a Xij, which are the covariance times beta. Beta are the fixed effects. Then you have a Vi, which is actually the random effect, and then the errors. That's a standard mixed effects model, and the random effects are basically same for every observation in a group. So Xij, I will assume a p-variate random vector of covariance. Beta is a p-variate unknown vector of regression coefficients. As usual, expectation of Vi is equal to 0. Variance of Vi is basically tau square, which is strictly greater than 0. Vi, Vj are independent for I not equal to j. Epsilon Ij are error associated with the observation of Ij. So expectation of epsilon Ij is equal to 0, and variance of epsilon Ij is sigma square, which is basically greater than 0. Okay, and we also assume that variance of Vi and epsilon Ij are independent for all I and j. This is a very standard assumption in mixed effects model. If you really have mixed effects model, you have groups, you have observations units in that group, and this is basically the model that you really want to fit. Okay, why is this important, and what is this small area estimation is all about? So the idea here is this: if you really run a big survey, suppose you are running a survey on the whole of US, and then it is, there are a lot of surveys which are actually run on whole of US, and then what you really want to know, that you have got the data, and then suddenly you want to say that, okay, let's for just for argument's sake assume that we are talking about, let's say, median income of people in US, and we basically run a standard at a survey and basically try to see that what are the median income. Okay, now what you want to do is, you don't want to really look at the median income in the whole of US. If the county that you are living, the county board suddenly says that, can you actually use this data from this survey and tell me what is the median income in this county. Now, if you, even if you, US is a very big place, there are more than 4,000 something counties. Yeah, so even if you have a survey which your sample is actually like, you collect like 15,000 or 16,000 data points, you are roughly getting on an average 3 points, 1 or 2 points or 3 points in your county. Okay, so that basically makes, an even it might even be zero, but let's assume that you have like 3 points. So essentially, even if you can give a point estimate of what is the median value, you, it is very difficult to give a estimate of the standard error if the accuracy is actually going to be very bad. Okay, and so the in small area estimation, what people do is they so try to say that, how do we really accurately do this from a like predict certain variables, certain whatever we are interested in, or let's say the median of the income in a small area, that is a county, from a big survey which basically doesn't have any small data. So the only idea here, only thing you can really do is that you can actually look at similar counties, the similar to your county, and then essentially just borrow information from there somehow. So if you have 3 points in your county, you can actually find similar, let's say 20 counties or 50 counties in the whole of US, and then you can basically say, okay, maybe I have like 3 points every county, that's about 50 counties, that's 150 points. Okay, you can give a better estimate of the median and its standard error. Now the problem of course here is that how do you define similar counties, and that is actually very difficult to do. The spatial closeness or spatial closeness always don't mean that the counties are actually similar. So for example, if you think about in US, you look at the inner cities, which is, let's say, let's for argument's sake, let's say Seattle, for example. Well, Seattle inner city, the county was called the King County, and if you really look at the county which is next to it, which is the suburb, they are actually two different counties, because in the inner cities there are a lot of, often there are a lot of poor people live. So the actual actually the median, if you compute there, will be low, but if you really go to the suburbs, most of the rich people live in the suburbs, so obviously the median income would be high. So the point is basically the spatial distance, the spatial character distance does not really mean that the counties are close. And frankly speaking, in small area estimation, there have been lot of attempts to actually include this spatial information, but that does not actually always improve the prediction. So the idea here is this. So what we really do in this random effect this VI is doing here is, it is just essentially basically it is basically introducing dependence on the data in the same unit, as well as from the data from the different counties. Though I have assumed that these are actually independent, often what they do is they assume a distribution on that, or a prior on VI, so that through those priors you will get some kind of dependence. So what is this thing is supposed to do is basically introduce dependence on different county level data, which kind of will basically make your prediction a bit better. Okay, so this is basically the idea under the what I mean by a nested error regression model, and what is basically under small area estimation. You can think about small area estimation, you can think about what is this model. This is basically just a mixed effects model. Okay, so the idea here is this. So what we know from our model, and this is very clear to see, but let's just revisit the mixed effects model a bit more. So without any distributional assumption or vi and epsilon ij, I'm not really going to assume that the following results would hold. Your variance of yij is going to be tau square plus sigma square, we all know that. And we know that the covariance of YIA and YIB, that is two covariance between the two observations in the same group I, is going to be tau square. Okay, so what you really do, so if in order to estimate the variance component in an unbiased manner, the estimating equation, what is usually do is tau square and this should be sigma square are constructed first. Then these equations are solved to obtain the estimates, and you know an estimate of the regression coefficient beta is also required. So what in Anaphobis method, what you do, we can use both weighted and unweighted least square estimator of beta, because here the variances are different. So you can either basically look at the beta which are unweighted estimates, or you can use which are weighted estimates, but two different estimates are often beta are often used for constructing estimating equation. The important part here is this. When we talk about variance component, we are essentially looking at more or less on these residuals, different kind of residuals. You use different kind of estimates of beta that is supposed to give you different kind of different residuals. Using those residuals, you can actually use sum of squares, residual sum of squares. You can actually use a great unbiased estimating equation for tau square and sigma square, and you can actually find values of unbiased estimate of tau square and sigma square. What is usually not used, and we were basically surprised that it was never really done, that you actually ignore this covariance information. Your covariance of yij and yib, that is actually tau square. So you can actually use this information also as an estimating equation, put in the tau square and basically solve for this. And that is something that we saw is not actually used. So let me give you how we construct these equations, and then you will see that how we can actually estimate them with using this covariance equation. And then I will show you what kind of properties you can have. So first of all, we will use unweighted ordinary least squares estimator, which is beta hat is equal to x transpose x inverse x transpose y. Yeah. So unweighted ordinary least square is beta hat x transpose x transpose y. And if you really look at the variance as covariance, let's define SI equal to just a yij minus xi transpose beta hat whole square, j equal to 1 to n. This is essentially your residual sum of residual square in the ith group. Your S is sum of SIs. And what I will do is I will define a, let's say it's a cross product, sum of cross products in the ith group, which is basically sum of cross product residuals in the ith group, which has ni greater than equal to 2, 0 is otherwise, and t is equal to summation ti. This is it. So essentially we will sum over a not a b, which is basically a not equal to b, this sum. Okay. So let's look at the we can how we can, using these two things, how we can estimate our variance components. So what I will do is I will ultimately write a unbiased equations for sigma square and tau square and basically solve them. So you don't really need to really remember this. The point basically here is that if you look at expectation of ti, you can write it as a tau square times something minus sigma square times something. What is this something is not really very important. Similarly, expectation of SI, you can say it can write about tau square times something plus sigma square times something. And then if you just add them up, you can write an expectation of T, which will also be an expectation of S, which are actually two linear equation with respect to tau square and sigma square. So essentially, if you tell me what is my expectation of Ti and expectation of Si were, which I will eventually replace by my observed Ti and my observed Si, I can actually solving these two equation, I can also actually solve for tau square and sigma square, right? So, and that is going to give me an unbiased estimator of tau square and sigma square, because these equations are actually unbiased. Okay, unbiasedness in estimating this tau square and sigma square is actually important. As you know that many of these estimators are not going to be MLE may not actually be unbiased. So people have actually talked a bit about unbiasedness, and people really, a lot of people really are actually stress about whether your estimators are unbiased or not. That is kind of important. Well, unbiasedness, there are some issues which we will discuss in a moment. So essentially what we really get here is that what I am writing here is that you have an expectation of Ti, expectation of Si, which are actually linear equations of tau square and sigma square. So the idea here is that you just substitute the left hand side of this equation by tau I and Si, and you can actually solve for this. So this actually gives you a way to include this cross product information or covariance information in your estimate of tau square and sigma square. So but there are some subtlety in here. So even our cross product terms, what we chose is basically kind of like natural, right? But there were some issues here. For example, when we talked about the way we chose it, and that is relates to this estimate of beta. Okay, so remember we use the unweighted estimator of beta. So you can show that your Ti plus Si is actually Ni squared times y bar minus xi bar hat square, right? This you can show. This is basically a random variable, but so that is the Ti plus Si is the between residual sum of squares, and this is a random variable, but that may not actually always be the case. So you have to be a bit judicious about it. So what you can actually do, what you could have used, there are other estimates of beta. What you could have actually used is, instead of using this beta, you could have used a beta hat, which is actually what you do is you essentially look at for the each area, I mean for each ith group, you actually subtract you do yij minus yi dot bar. You write this equation as a yij minus yi dot bar xij minus xi dot bar transpose beta, and then essentially what happens is vi actually gets subtracted out. You get epsilon ij minus epsilon I dot mean as well. So if you really do that, there is a reason for doing that. You can see that then their vi is not really there, so there is no random effect. So you can actually, using that equation, you can directly and unbiasedly estimate the error variance. So if you really look at that, this is what Prasad-Rao estimator does. If you use the within residual sum of squares, this is exactly what you are going to look at. This is your S tilde. Beta hat is basically estimate if you have subtracted the area means from that area observations, and beta hat, of course you will have to use a generalized inverse of this matrix, which is not going to be invertible anymore. But you can actually, but then again, if it's a generalized inverse, there are projections and etc. So your estimates are going to be invariant. So I will again look at it in a moment. But anyway, so but what you can actually do is you can actually calculate S tilde in this way, with this beta estimate of beta. If you actually do, your expectation of S hat will not depend on tau square, and that is basically a great advantage. And I showed you why, because your VI gets actually subtracted out. Now, if you now look at now in this construction, that means that if you take this sum is always equal to 0. So what you are really doing is basically you are looking at the residual sum of squares, and you will actually look at this is equal to 0, which basically ends up into, this is 0 because this sum is 0. This is because this sum is 0. You are essentially just adding the residuals when the sum of residuals are actually equal to 0. Then you take a square, you take a sum, it does not going to give you anything. So the corresponding T tilde, if you actually calculate, you will see that T tilde is going to be minus of S tilde. So your product, the cross product terms, are not really going to give you anything extra. Okay, there is no extra information. So what I actually said that yes, you can actually use this cross product, but you have to choose your beta hat and all these things carefully. Otherwise, the cross product term is not really going to give you anything extra. Okay, so now let's assume what we set up. Our beta is still basically beta hat, and I have these results. And let's now try to look at this. So essentially what we are going to do is we first look at what we call the combined estimator. That is basically you sum all the SIs and T's first, you will get an equation, and you actually solve it. I will call it the tau square, tau hat square A. Now, one of the thing about ANOVA estimate is that this is basically, if you just solve these two equation, you get tau square A is equal to this. This is the solution for tau square. One of the problem with ANOVA estimator is that your tau squares and sigma square, the estimates that you are going to get, that may not actually be positive. You may get negative estimate. So people, what they do is they basically use a truncated estimator, which is basically tau square A is equal to maximum of 0 and tau square at sigma that we have talked about. So if this is negative, you just take it equal to 0. Okay. Now, one thing you notice that if you really look at tau square A, this is actually unbiased for tau square, but it can be negative, but it is unbiased for tau square. Okay. Now, the estimate that is also used here, which is called the Prasad-Rao estimator, it is an estimator for any estimator of sigma square. We can solve equation 10. This is my equation 10, and you can show that you can actually and 11 and obtain adverse estimator of tau square. We showed that the Prasad-Rao estimator sigma square is given by using S tilde, and you can show that this is also unbiased. So this is defined by S tilde divided by total number number of sample size minus number of groups you have minus the rank of that matrix B, which we use to invert to define beta. And then you can again, there is no guarantee that you can, and now with this sigma squared, if you substitute in this equation, you can get a estimate of tau square, and we can show that again this is not always defined to be positive. So if it is negative, you can do a maximum of 0 and tau square hat. This is basically it. So tau square hat PR is an ANOVA type estimator. If you are familiar with this lingo, again we will get into that in the later. These are called basically Henderson 3 type estimators, method 3 estimator. Okay, so we can do another estimator. This was combined estimator where I actually used SI and S, added all the S's and added all the T's, and essentially solved the added equation. What you can actually do is you can actually solve the equation in every group when the number of observations is greater than 2. You can solve every group, and if you, after solving every group, you can actually look at tau y square, and then essentially you can actually take the mean of those estimate. These are actually, I will call these a separate estimator. So, and again, these are essentially, this is basically like if you are familiar with stratification in sample survey and you are looking at regression estimator, sometimes you use the combined strata, you sum everything and then solve for your regression estimate. Sometimes you actually do it in every strata and somehow then take an average or something. So these are basically connected to, similar to that. So obviously what we did here is that you just basically estimate your tau y square in every group and then just take the mean. This m minus m1 is basically just the number of your m1 is probably the number of you actually need to have a number of number of areas where you only had one observation. This is just a technicality. So again, tau square s is not actually, but what you do is you take the it's not guaranteed to be non-negative, and if it is negative, you just take it to be 0. Now, another way to do this is that if you have two asymptotically unbiased estimator of tau square, you can combine that. And the combination works in this way. What you really do, suppose tau 1 hat and tau 2 hat are the two asymptotically unbiased estimator of tau square, and you combine it as a weighted estimator. So tau square 1, 2 will be some weight times tau 1 square and plus 1 minus. So you basically 1 minus that W tau 2 square. W is between 0 and 1. This is basically a convex combination of it. And what you the weights we don't know, we have to estimate the weights, and that is actually optimal weights are determined by minimizing the mean square error of W tau 1 square plus 1 minus W 2 tau 2 square minus tau square. That's whole square of that. So if tau 1 square and tau 2 square are, if they are even asymptotically unbiased estimator of tau square, you can show that W is actually given by this formula, which actually turns out to be W being W hat star is being maximum of 0 and minimum of this, which is actually if tau 2 hat square is less than tau 1 hat square is 1, if tau 2 square is greater than tau 1 hat square. So essentially what you are doing is tau 1 2 hat square is basically the minimum of these two estimates. Okay, this is somehow approximately becomes optimal actually. So what you can do is we can actually define, using this method we can actually define more estimates, and what we will do is we will take the minimum of tau hat square PR and tau hat square A, which we will call tau hat square PRA, tau hat square PR and tau hat square S, which we will call tau hat square PRS, and then take the minimum of tau hat square A and tau hat square S, we will call it the tau hat square AS. Okay, so basically the idea here is that I basically looked at these equations, I just solved it, and essentially my target here is to compare all these estimate with this Prasada Rao estimator tau hat square PR, which is actually kind of used in small area estimation very frequently. The reason, one of the reason why this is used in small area estimation, the Prosaradao estimator, since it actually gives you a closed form solution, it is actually easier to handle it. It is easier to compute, and then it is easier to compute is ms mean squared error, etc., which you can actually get in a closed form. If you are looking at MLEs, it is not really very easy to do. If you really look at, and traditionally you can use the MLEs, but essentially if you want to estimate it or work with it, you can probably estimate the mean square error using your essentially using the Fisher information matrix, etc. But doing anything theoretically or looking at how it behaves theoretically becomes very difficult. So sometimes Prasad-Rao estimators are actually studied very it has become popular because you can really look at his MSE and things more easily, as we will show in a moment. So okay, so let's look at some of the properties, asymptotic properties of our estimator. So since we are looking at variance estimation, variant components estimation, if we look at his asymptotic properties, we are talking about fourth power, that is the kurtosis of the distribution. So what we will do is we will look at the kurtosis. It will become important, the kurtosis of the error random effects, and the errors will become important in a moment. But what we do is, instead of actually looking at the actual raw moment, the fourth moment of the random effects and the errors, we basically kind of standardize them a bit. So essentially expectation of V4 is written as 3 plus kV times tau to the power 4. This is because if your V is normal, then kV is equal to 0. That's basically the idea is, and you can see that the expression will turn out to in terms of kV, and you can actually see what it is actually a bit easier to look at. We will basically look at, if your Ni, when Ni is greater than equal to 2 and my number of Ni's are bounded, the number of sample size in every group is bounded, but the number of group goes to infinity. We are more interested in random effects. So obviously if your number of group goes to infinity, you have more observation on the random effects, so you can actually you should be able to estimate your random effect variance more well. We also assume X is of full rank and X transpose X divided by n converges to a positive definite matrix. These are more or less technical conditions, what kind of moments actually exist or what would be the order of those moments. These are a bit technical condition, but we will basically just assume that. If you do it, if you look at the asymptotics, all these asymptotic variances were computed by Tatsuo. By the way, it's actually pretty complicated, tedious calculation. You can do it. It's not. I mean, it's pretty tedious. It's actually not very easy to get them. But anyway, if you really, for large values of m, you can show that the variance of expressions are like this. Again, the expression as such is not really very important. What is actually important here is that if you look at the variance of tau square PR, this term, the kurtosis of error random variable, the kurtosis of these two error variables, that actually appears. Okay, variance of tau square S and variance of tau square A does not actually have this error kurtosis term. It depends only on the kurtosis of the random effects. Okay, variance of tau square A, tau square S only depends on the kurtosis of the random effects, and tau square hat PR actually depends on the kurtosis of the random effects as well as the error. Okay, this is actually significant. The reason it is significant is that it is notoriously difficult to estimate the kurtosis. Kurtosis, if you really can want to estimate this variance tau square of tau square PR, you need to estimate the kurtosis of the errors as well as the kurtosis of the random effect. For tau square, if estimating the variance of tau hat square A, estimate of the variance of tau square hat square S, you don't need the kurtosis of the error. You only need to estimate the kurtosis of the random effects. Estimating kurtosis is actually notoriously difficult. You might think that you are essentially estimating a fourth moment. How difficult it can be, you just basically take the fourth power of whatever random variable you have and take its mean. That is not really going to give you the, it will give give you an estimate of the kurtosis, but it is not going to give you an accurate estimate of the kurtosis. So the kurtosis, estimation of kurtosis is actually pretty difficult. If you can avoid it, it is better. So one thing, another thing is that if you look at the tau square a and tau square s, and if you really look at this asymptotic variance, it does not really depend on the variance of the error random variable. So if your error is not normal, it will affect the variance of the tau square pr, but it is not going to affect the tau square a or tau square s. Okay, so this is actually a very interesting result, that if you can use the covariance information, it actually gives you something. It is not that we are essentially, it is gives you some kind of improvement. It is, in that sense, it is actually robust, because it does not really depend on the distribution of the errors. It depends on the distribution of the random effects, and you have to have that in there. You cannot avoid it. But unlike tau hat square pr, it is not going to depend on the estimate of the error variance. Okay, now how about my okay, these were, if you look at it, these were actually the estimate uh, of the unbiased estimator, which can actually be negative. What about the maximum of 0 and this unbiased estimator? Under the assumption in A2, you can actually show that this, when m is large, the variance of tau hat square a and tau hat square tau hat square a star, though both are going to be more or less is the same. It is actually smaller of 1 by m, so it is basically going to be similar very quickly. And this is true for all the estimates. Okay, so also also you can show that this is the one of the case which people look at. So what you can actually show assumption in a1 and a2, the estimator tau square a, tau square s, and tau square pr are rutium consistent. You can show that. And in the balance case, which a lot of people actually look at, and that is basically the case where the Prasad Rao estimator works the best. So in that case, the asymptotic variance are all the same, and in the balance case, the asymptotic variance of the Prasad Rao estimator is not going to depend on the error kurtosis either, so it can be reduced to this. So this is basically when the case is balanced. If it is not balanced, you will actually get into this situation. Now let's look at a bit more. So this is the third proposition. If you look at the asymptotic variance under A1 and A2, you can actually show, again, I won't, this is basically the asymptotic variance in the limit when tau square it goes to 0. Remember, tau square was connected to the correlation between the observations in the same group. If that goes to 0, which means the correlation is actually going to 0, uh, hold on, what did I say? Yeah, if it is going to 0, did I say it correctly? Tau squared by yeah, okay. So if the correlation is going to 0, that means in that case these variances take this form. And moreover, when ke, your error covariance, is equal to 0, you can show that the asymptotic variance of tau square a is going to be less than the asymptotic variance of tau square pr is less than equal to the asymptotic variance of tau square s. So what is essentially it is saying, when the random effects variance is actually small, then tau square a is going to be more efficient. Okay, now when the sigma square is going to 0, that means actually which actually means that your correlation between the observations are actually going to 1, then the opposite things happen. Then the asymptotic variance of tau square s is actually smaller than the asymptotic variance of tau square at pr, and is less than the asymptotic variance of tau square a. So basically what happens is, when your correlation between the observations are actually large, then the asymptotic variance of the tau square s is more efficient estimator. Okay, you can also show that in the case that tau square s is greater than goes to 0, asymptotic variance of Prasad Rao estimator is actually increases as the error variance increases, which was actually clear from the observation of the expressions we had. And so when tau square is going to 0, it actually holds that asymptotic variance of tau square a will always be always be smaller than the asymptotic variance of tau square PR. This is true because if your if ke actually increases, it is going to, this side is going to increase with ke, and this is actually invariant. It is robust. It doesn't depend on ke. So what actually is, it's a very interesting result in some sense, that you actually get to see when you actually want to use tau square a, when you want to use tau square s. Of course you need to have some sort of estimate of what is the variance here, but you can see that there are something going on here where the product of the all these estimates actually of the using covariance information actually makes gives you some advantage. Okay, what happens to, now the question is what happens to, so if you, so if tau square PR increases with ke, is means that if you have a t distribution, the variance of tau square PR would be larger than the error when the error has a normal distribution. That's basically what it is. And you can see that if you under the relationship, this asymptotic variance of tau square a is less than asymptotic variance of tau hat square PR, it will always hold. Now, for the combined estimators, tau hat square 1, 2, which were the minimum of tau hat square 1 and tau hat square 2, remember, you can show that this relation holds. So, expectation of tau hat square 1, 2 minus tau square square, this is basically less than equal to expectation of this square and individual squares, which actually means that under the proposition 2, the estimators of this estimator will be actually root m consistent, because these are root m consistent. Okay. So now let's look at an ad hoc estimator. So why we did this, why we went into ad hoc estimator. This you can actually show that our method somehow beats the tau square Prasad-Rao estimator. I will show you some simulation where we can show that it actually beats, but you have some estimate like this. There is one question actually comes up, that what happens with the MLE. We are, so initially when we actually did this work, our idea was to try to beat the Prasad Rao estimator, whether we can beat it. Okay, we can kind of beat it in some way. We will show you show you some simulation where it actually works. But what about the MLE? Can you actually get an estimator which basically would say that I can beat the ML or REML estimator from there? Okay, can that be done? Okay, so I will give you an ad hoc estimator. We have not really studied its properties that much, but in the simulation it actually looks very good, and it actually really beats the MLE to some extent. So I'm going to really present it. And here there is a interest. I mean, let you some of you will already get it what I am doing, but let's explain this in a bit of a details, because I think I still have like 15 minutes, right? So I will just describe it what we are doing. So look at our model. My model is y equal to x beta plus z times v plus error. I am using a general z, but my z in here is basically a column of ones, just basically group indicators, but you can do it for general z as well. Now, when you talk about restricted, if some of you would actually already have seen this, when we talk about restricted maximum likelihood estimator, what you actually do is you actually multiply both sides of this equation with a set of a matrix whose columns are orthogonal to x, right? The column space of x. Okay, so basically what you do is, so the idea is that in that case h times x will be equal to 0. So you can look at h times y equal to will become h times z plus h time error. You can take h in such a way so that h transpose h is basically this qx, um, your if I minus the projection matrix on the column space of x. H transpose is I, which actually means that your error variance is not really going to change, because the error variance is going to be h transpose sigma squared, so that is basically sigma squared. So the error structure is not going to change. So when you talk about REML estimator, what you really do is you look at this equation, You have the error variance, you have the error distribution for the errors, you distribution for the random effects, both are normal, and now you basically calculate the maximum likelihood estimator of the error variance components using this estimator. So what the good thing about this is you don't need to bother about beta. Okay, you don't need to bother about fixed effects. Okay, now Henderson 3 method actually does the same thing. It basically multiplies, looks at this equation and essentially creates an ANOVA based estimator from this equation. Okay, so that you can show that if you really look at this, okay, the Prasad-Rao estimator was actually used this equation. What we actually did in Prasad-Rao estimator, instead of getting rid of x, you got rid of z. You multiplied by y by a matrix which was actually orthogonal to the column space of z. That was, I will go back here, this, when you talked about subtracted y bar from each group, y bar and x bar of each group, it is actually equivalent to multiplying everything with a matrix which is orthogonal to the column space of z. This is not very difficult to see, and the point is what you actually got by doing that was that estimate of the error variance, and kind of an estimate of beta hat. You could have done it in this way as well, in the sense that got rid of the column space of x first, and then you would have v and error, but it will give you the same estimate of the error variance. Okay, I will get back to it. What is the difference between what we are doing and how you estimate the random effects variance? Okay, so now let's look at this equation. So the idea here is this: I have hy, which is equal to hz times v plus h error, right? And now let's look at this as a regression equation. It's a regression, right? And your v's are actually regression coefficients in some sense, right? So what I will do is I will estimate the regression coefficient. That is going to be z transpose qxz, a generalized inverse, times z transpose qxy. No problem. I am using Moore-Penrose inverse. I am using a specific inverse. Okay. Now look at v. Okay, v hat, and let's try to find out what is the expectation of v hat square, v hat transpose v hat. Okay, you can show that that is equal to tau square times the rank of z transpose qxz plus sigma square times trace of z transpose qxz plus, that is the Moore-Penrose inverse. Okay, now as I argued that if you actually solve for sigma square here, you try to estimate sigma square here, it is going to be sigma square hat pr. You can show that it is just taking same projections in two different order. When you talk about sigma square hat pr, you take first projections with respect to z, then a projection orthogonal to the column space of z, then that projection of that to the orthogonal column space orthogonal to the column space of whatever this x then is. Here you are doing it in the opposite order, nothing more than that. You can show that your sigma square is going to be sigma square at pr. So if I substitute this and actually solve for tau hat square, you will get a tau hat square v, I will call it that, which is basically given by this. Okay, so what we do is, this is my tau hat square b. Again, there is no reason to believe that this is going to be non-negative. So we take maximum of 0 and tau hat square b. And also for empirical evidence of simulation studies, which we'll show in a moment. If you take the combined estimator, which we'll call the tau hat square pr b hat, which is the minimum of tau hat square pr and tau hat square v hat, that kind of shows a good performance. Our tau hat square v is actually differs from the Prasad-Rao estimator tau hat square pr. Okay, the Prasad-Rao estimator is obtained by solving the estimating equation obtained from the square of the length of the projection of hy on the column space of hz. This is a purely Henderson 3 estimator. If you look at so you have looked at this, now you want to look at tau hat square, you look at hy, you project it on the column space of hz. That length of that projection will actually depend on v tau square, and you use that to estimate. Okay, The proposed estimate is obtained from the expectation of square of the length of the least square estimate of V. So we are doing two different things here. One thing why you actually do in the column space of HZ, the one of the thing is that since you are looking at projections, Prasad-Rao estimator is invariant to the choice of the G inverse. I have used a specific G inverse here. Prasad-Rao estimator is going is because it depends on the what on the regression estimates. Okay, regression coefficient estimates of the regression coefficient depends on the choice on the G inverse. The projections actually don't. So Prasad-Rao estimator will be invariant to the choice of G inverse. My expectation of 26 depends on the properties of Moon-Penrose inverse of Z transpose QXZ. If you don't want to use Moon-Penrose inverse, you use and some other inverse, it will actually be different. But I'm sticking to the Moon-Penrose inverse. It has kind of good properties. It is smallest length. It will have smallest area. It's a fine thing. Okay. I won't have the time to go through some estimators of the error variance that we get here, and I will basically skip it. They are not really that exciting in the sense that it is we can construct some estimators which are more efficient than the Prasad-Rao estimator, but it is just I will show you some simulation. It is just slightly better than Prasad-Rao estimator. Prasad-Rao estimator is actually a very good estimator of sigma square. That was it was designed to. When you actually got rid of this random effects model, random effects here, you were actually estimating your idea was to estimate sigma square. So it is actually a very good estimator of sigma square. Uh, and that is because the way it is constructed, you got rid of your random effects variance, so only variance you have is actually this estimate, which you can actually estimate very accurately, okay, unbiasedly. So I will basically get rid of all the error variance stuff. Let me go through the simulation study. So we have two things here. One, everything is normal. Another is everything is T distribution. And I have taken the degrees of freedom for T distribution k equal to 5. Okay, which is basically which has kurtosis which has a finite kurtosis. If T is greater less than 4, there you won't have finite kurtosis. And I have two different patterns. One ni is they are actually the same size. This is the balance case. Another one where the ni linearly grows, and then another one where the ni is kind of linearly grows, but we have another group which has very high sample size. Okay, we have three covariates. Sigma square is taken to be 5, and we report results for tau square from 0 to 0.1 up to like 10. Okay, fixed effects are xij's are generated from multivariate normal, and the covariance of values of xij's are covariance with a covariance, and the betas are fixed at -1 to -3. These are basically just standard ways. So if you really look at the tau square balance case, you can see that Prasad-Rao estimator kind of works the best, roughly works the best. Your tau square A is slightly better when this is 0, but Prasad-Rao estimator, tau square, these are more or less Prasad-Rao estimator was the best. If you actually look at those two unbalanced case, this is the case B, you can actually see that if you really look at tau square AS, it is actually much better than the Prasad-Rao estimator throughout. Okay, even for normal distribution. If you really look at, so tau square AS and tau square PRS, they are basically the best. If you look at, it is working better than the Prasad-Rao estimator in both in normal and T for T distribution. If you look at the tau square PRV, okay, you can actually see that even for all cases, mostly it is actually going to beat the Remel estimator. Here, the maximum likelihood and the Remel estimator are basically very close. You can see that it is going to beat the Remel estimator quite close, quite a bit. Okay, in this case also it beats the Remel estimator, and obviously beats the Prasad-Rao estimator and everything. So what we found is that chi-square PR V hat is actually the best, but even if you look at the Prasad-Rao estimators, our estimator AS, those PRS AS, the estimators we are constructed, they actually work quite actually well. Okay, if you look at the balance case, even then also your tau square PRV, that is actually better than the Remel estimator as well. In fact, it is better than the Prasad Rao estimator as well. Okay,
Sanjay, sorry
just
to
yeah,
interrupt. You have like about 5 minutes.
yeah, I'm done. I'm almost done. So I won't go into this sigma square result for sigma square, sigma hat square. You can look at the paper. It is actually there. Well, the paper, if you need, let me know. I can send you the paper. It is there. But these are essentially shows that sigma hat square PR. The Remel estimate, the Prasad Rao estimator is actually a pretty good estimator. So we didn't get that much into from here. Anyway, so the whole so you can actually, so this is basically essentially the last slide. It is a application to the small area estimation, and this was actually about the house price, land price data along what is a KQ line in Tokyo. So if you are actually been to Tokyo, there are a lot of private railway companies in Tokyo which operate, and this one operates in the Kanagawa prefecture. And what you really have here is that what is the land price. You have, look at how long it takes from the train from station I to come to Tokyo station around 8:30 in the morning. This is basically the commuting crowd. You have that time square as well, and then you look at the walking time from the spot to the nearby station. Of course, that will also be a covariate, and then how much is the floor area, right? And we did this, added a random FX model VI, and then this is the error epsilon j. If you really look at this, this is basically the here actually, unlike the simulation study, we actually have a intercept term. Okay, so now if you actually look at it, it is important because of this z. Their z is, if you have an intercept, your the if you look at the z, if the columns of this intercept term is basically in the column space of z. So essentially, if you look at, you have to, if you look at it, look at this structure here, that actually matters here. Okay, for this estimate, it actually matters. Anyway, so if you really look at this, we found these betas to be like this. And if you look at the sigma square a, you can see the sigma square a is like 0.02, but all the sigma square, other sigma squares are, estimates are actually almost the same, 0.0211. These are basically very close. If you look at the tau square PR is 0.008. It is very small. Tau square a turns out to be 0.01, roughly 0.009. Tau square PRA, which is basically minimum of this and this, which will turn out to be tau square 0 s. And actually you can show that tau square s, which is actually smaller, which turns out to be 0.005, and tau square had PRS and tau square had AS. I somehow forgot to put in the values of these V estimators here, but they are actually also pretty close. Okay, so I will stop here. If you have any questions or comments, please let me know. Um, uh, if you so that's basically it.
Yeah,
Okay.
thank you, Sanjay. I think we are a little bit over time, so maybe some folks have left. I had
Okay.
a very quick question. So, at the very beginning, you mentioned that like including like when you're trying to estimate these random effects in a small
Okay.
area estimation type of a setup,
Yeah.
including like if you're trying to estimate these for incomes for different counties, if you're including spatial neighborhood within as
Yeah.
a structure within the
Yeah.
estimation, that might not improve the prediction overall, right? So I agree to that to some extent, but I also think that depending on what granularity of spatial interaction you're looking at, it like does it impact at all
Okay.
if
Good
you're not.
question. Actually, it's a good question. Okay. First of all, if you really want to, it is not very clear why that does not work, including spatial information, why it doesn't work. Now, people have tried that, but my experience is most of the cases people say that, yeah, we tried, but it didn't work. There is only one paper I know which came out in JSPI. I think it is basically Scott Holland. uh, Weikel, they basically did that. And their idea was that they actually look at some county level data near Portland, Oregon, Portland, and they kind of showed that it can actually be done, but it might improve. So it probably depends on the data. So pretty much depends on the data. So as I said, in survey sampling, spatial uh, proximity does not really mean that it is going to be that correlated, right? You can actually really look at one side of a hill and another side of a hill. It's basically, it's might be pretty different, right? So,
Mhm.
or one side of the river with another side of the river. So that sort of things, if you really just do with spatial proximity, is not probably going to work. Okay. Another
Mhm.
thing is, if you, the states might actually be very different, the counties, the states, all these things might actually be very different. So how you are doing it, it's actually a complicated thing. But I mean, everybody thinks that it should work somehow, but very few places I have seen that it has worked. I mean, that's what I would say. I mean, of course, there
Um,
are one or two papers where people have shown that it might work, but if it works, but
yeah,
so
my thought process was more like if you're looking at a much more granular level, like maybe like a zip code or even a smaller granularity, they would probably be similar compared to
yeah,
expecting
but
two
you need
counties to be
then.
dissimilar.
Yeah, but in those cases, you need a zip code. You need a really zip code level data. If
Mhm.
you the examples that you are looking at, getting zip code level data is not very easy. You don't really get. Nobody is going to pay you for that sort of a survey. It's the
Mhm.
now even so only. More or less, the only hope, I think, turns out to be they do some sort of a short form CPS, current population surveys and all this stuff, or national households panel survey, that sort of things, which might actually, CPS is not really very accurate. I mean, one of the model here, which it's not really this type of model. There is something called an area level model, where you don't really have unit data. You essentially just only one data point per county, that sort of thing. In those cases, its CPS turns out to be very inaccurate. That was something that motivated all the small area estimation to some extent. The thing that I showed, this nested error regression model, it is actually due to Wayne Fuller and his colleagues, this Betty Harter Fuller, and they were looking at in some crop survey data in Iowa. So what you do is, you essentially look at, like, take pictures from helicopter about the Iowan fields. And in Iowa, I have never been to Iowa, but people say that if it is either corn or like maize or some soybean or something, and they basically want to say that how much acreage is there under soybean and under corn. So you take picture and then you send people to the field and to find how, whether this field is growing corn or soybean. That is actually expensive. Taking pictures from satellite or helicopter is probably better, easier. So they basically try to do this. That was, there you can actually get more than one observations per county. But even then, even the data that Betty Hatter Fuller used, there are counties which actually had only one observation. So it's not, it's not always easy to get this. Like
Mhm.
nowadays, probably you can get, if you look at house prices data, you can get the whole thing from Zillow, I guess. You can just put
Mhm.
Zillow and basically say that, the Zillow is basically predicting the house price should be this, and then and you can look at the court records and find out at what price that house was actually sold. So that sort of things you can actually do. But in general, getting from a sample survey, getting a zip code level data probably is not very easy, as far as I know.
Mhm.
So so that's basically what it is. You can get
Thank-
it from sensors though, but I'm not very sure if you can get it from really surveys.
mhm.
So
Thank you. Any other questions? I
there's
know we
only,
are way over time.
okay,
Any last questions?
anyway.
Just want to thank Sanjay for a fantastic